So, now let us move to a question as to whether multiple extractions are better than a single extraction. A simple way to rephrase this problem will be that I have a compound that is dissolved in 20 ml water, and I am undertaking a solvent extraction of this compound using a particular organic solvent, for example ethyl acetate, and we use 60 ml of ethyl acetate in one go and undertake an extraction, or we can do extraction 3 times with 20 ml ethyl acetate each time. And the question in front of us is that which of these two protocols is better or is more efficient in extracting the compound from aqueous layer to the organic layer. I will give you the answer to begin with, and then I will try to explain you mathematically how this happens. So, what is well known is that the second condition where we are undertaking extractions multiple times is much more efficient than the first condition where the extraction is happening only once, even though the total volume of the solvent that we have employed is same in both the cases. So, volume of the solvent is invariant in both the conditions, but extraction multiple times is considered or is more effective. Now, let us see how this happens mathematically. So, let us go to the board and let us start with a presumption that we have initially m naught mass of solute which is dissolved in V aqueous volume of aqueous phase. Now, we extract it with V organic volume of organic solvent and allow the equilibrium to be attained. Now, when we do that, we will define the K d as equal to the concentration of the analyte in organic solvent divided by its concentration in the aqueous medium. Now, m1 is the mass that remains unextracted. So, please note that m1 is the mass that we consider to be remaining unextracted. So, we can define Kd as equal to m naught minus m1. This is the amount that is getting transferred into the organic layer. This will be divided by the V organic, because we are extracting it with this volume of the organic solvent, and this will be divided by m1, which is the mass that remains unextracted in the aqueous layer, divided by V aqueous, which was the volume of the aqueous layer. And when we rearrange this, we get m naught by m1 is equal to is equal to 1 plus Kd into V org by V aqueous, and finally rearranging it gives us the unextracted mass as equal to the initial mass of the solute divided by 1 plus Kd V org by V aqueous. So, this is the mass that remains unextracted after first extraction. That is given by m1, and that is equal to m naught by 1 plus Kd into V org by V aqueous. Now, suppose we undertake the same extraction the second time, what we get is extracting the aqueous layer the second time, with V org volume of organic solvent and allowing equilibrium to be attained. This gives us the m2 now is equal to m1 divided by 1 plus Kd V org by V aqueous. So, please note here that in the second extraction we will be initially dealing with the m1 mass of the analyte present unextracted after the first extraction, and that is extracted with V org volume of organic solvent. So, the mass that remains unextracted after second extraction is given as m2, and we have already seen that m1 is nothing but m naught by 1 plus Kd V org by V aqueous. So, when we insert this value of m1 into the equation 2, we get m2 is equal to m naught by 1 plus k d v org by v aqueous squared. Now, if we keep doing this extraction for I times, with V organic volume of organic solvent, then what we have is that the mass that remains unextracted after these repetitions of extractions is given by mi is equal to m naught divided by 1 plus k d into V org by V aqueous to the power of I. So, this becomes the mass of solute that remains unextracted. Now, we can rewrite this as m naught by m I is equal to 1 plus k d V org by V aqueous to the power of I. Similarly, if we are doing in condition 2, we are doing a single extraction by I into V org volume of organic solvent. So, the example that we were discussing, this I into V org will be equal to 60 ml of the organic solvent, while in the condition 1 we were extracting 3 times with V org of 20 ml. So, the total volume that is being employed for the organic solvent remains constant in condition 1 and condition 2. Now, when we do this single extraction by I into V org volume of organic solvent, we will consider the mass that remains unextracted as m dash is equal to m naught by 1 plus k d into I into V org, that is the total volume of organic solvent that is being used now, divided by V aqueous. Now, this equation 4 can be written as m naught by m dash is equal to 1 plus k d into I into V org by V aqueous, and this we will consider as equation 5. So, what we see here is that as per equation 3a is what we define this equation as per equation 3a, m naught by mi is equal to 1 plus kd v org by v aqueous to the power of I, and if this is expanded, this becomes as 1 plus I into kd v org by v aqueous plus I into I minus 1 2 factorial into kd v org by v aqueous squared, and the other term here would be I into I minus 1 into I minus 2 by 3 factorial multiplied by kd v org by v aqueous to the power of 3, so on and so forth. So, if we see the first two terms of this expansion, this is nothing but m naught by m dash as shown in equation 5. So, in other words, m naught by m I is equal to m naught by m dash, which was the mass fraction that was remaining unextracted after the single extraction, plus extra terms which are given as the square and the cube terms. So, what we see here is that m naught by m I will turn out to be greater than m naught by m dash, or in other words, when we rearrange this, m dash will turn out to be greater than m I. So, the extraction single time with I into V org volume of the organic solvent results in more amount of solute that remains unextracted in the organic layer compared to the same volume of organic solvent used multiple times. Now, let us look at this from a real examples perspective. So, for that I have taken the example of paracetamol, and this is of course a very commonly employed drug, and I am sure all of us would have taken paracetamol at some point of time in our lives. And paracetamol is known to have a log p value of 0.49. This is a literature value, and what we need to consider is the question that is given in the example here, that paracetamol has the log p value of 0.49 and an aqueous solution containing 0.4 gram of paracetamol in 50 ml is extracted with 40 ml octanol. So, the question for us is, if we use this 40 ml octanol in one go, how much is the paracetamol that remains unextracted? And the other condition that we will employ is where we use 2 extractions with 20 ml octanol each. So, the total volume still remains 40 ml of octanol that is used. In this condition, how much of the paracetamol remains in the aqueous layer? So, let us try to solve this question by going to the board. So, we are given log p value as 0.49, and from there we can calculate the p value is the anti-log of 0.49, and this turns out to be 3.09 as the p value, or in our parlance this will be the Kd value as per the discussion that we are having. Kd value specifically for the partitioning between octanol and water. So, here condition 1 tells us that we have the V org as equal to 40 ml and the V aqueous is equal to 50 ml. Now, Kd is defined as the concentration of PCM in octanol by the concentration of the drug in aqueous medium or water, and this will depend upon the mass that gets transferred into